last time we generate this file for the test bench for this model here, n-bit add sub. So now let us simulate the functionality of the n-bit add sub. So we can launch our ModelSim. So launch ModelSim. So we are here at the ModelSim now. So what we need to do, we need to go to compile. Compile. And then we need to compile the test bench file for n-bit add sub and the model n-bit add sub. Compile. Done. So you can go to work. You can see it imported all the hierarchy models. For example, it imported the ripple carrier adder, full adder, and half adder. So there are hierarchies. So all of the file must be correct. So now we need to simulate this n-bit add sub. Simulate. And add all the signal to wave. But now we'll mostly look at transcript. So let's do it. And then simulate in nanoseconds. Simulate all of them. Simulate all. No. Now we can see, let's look at transcript. It's easier to look at this way. Let's make it a little larger. Now, for example, we can see here we have all of our combinations. For example, if we go to at the beginning, we have the addition here. So we have all the combination for addition. And then from here, after we finish all the combinations, we are having subtractions and then all the combination for the subtraction. So this worked well as we intended. It doesn't show any errors here, but there's some error that if we are interrupting all the bit as unsigned, no problem. But if we assume that we are using a second complement, then we'll have some issue here. For example, if you look at, for example, 7 plus 1, if you assume that is the second complement, is not minus 1. So this is wrong. So let's explain this at the board. So now, if we are assuming we are using second complement numbers, so if you are using second complement number, so for example, we look at the example 7 plus 1, so 7 0 1 1 1 plus 1 is 1 0 0 0. So this is 8 generally, so but in second complement it's not. So it's 2 0 carry 1, so you're carrying 1 here, 0 0 carry 1, 0 carry 1, and then 1, and we have a carry of 0. So here this one is minus 8 in second complement, and it's not true. 7 plus 1 is not minus 8 in second complement. So you can see that we have an issue. Why we have an issue? Because if you remember this formula that we have, if we are using 4 bits, 4 bits numbers, so the range is -2 n minus 1, 2 n minus 1 minus 1. So the range is -8 plus 7. So the answer should be in this range, else that means you have overflow bit. So this is wrong. Let's look at another example. For example, if you look at the -7 and -2, so in bit this is gonna be it is 1 0 0 1. So this is plus -2, it is 1 1 1 0. If you do the addition here is 1 1 1 0, and then we have a carry out. So we can see here, so this is not true because it say -7 plus -2, it is equal to 7, and then this is not true because it should be -9, but it's out of range. That's why we are having wrong answer. So this is not +7, it's not equal that. So that means we have overflow. So if the number is out of this range, it means that we have overflow. So how will you detect overflow? So let me write overflow. There are several ways to detect overflow. One way is to look at the, for example, at the carry outs. So here we see we have a carry out. So if you look at the last, for example, this C3 and this one is C4, if those two are not equal, if carry out 3 and is not equal to carry out 4, so that means we have overflow. So it means that is overflow. So let's take example that we don't have overflow. For example, if we take 7 plus, so -1, which is, so this is one is -1. So if we sum this all, we have 0, and then you have here it's 3. So you have a carry here. So is 1. So you have a carry here is 1, and then still you have a carry here. So you have 0 and you have 1. So you can see here this one is 7 minus 1 is equal to 6. So you can see here we have a right answer, but look at the carry outs. Here the C3, which is this one, C3, and the C4 are equal. So if C3 is equal to C4 is equal to no overflow. Another way to look at overflow is to look at the last summoners. For example, here, if you have, so you can say overflow is equal to, for example, the last 2 summons plus the answer. If you have positive number and positive number, but the answer is negative, you have overflow. So if the last summoned x3, so you can see this x, y, and sum. So if x3 and it with y3, those are positive, and AND it with the invert of sum 3. So if here is negative and those are positive, you will have a 1, so that means you have overflow. And another way to look at it, if again overflow, if you have negative number, so if those two are negative, this is negative, negative, and you have a positive number, so that means you have a flow. For example, if this is negative, negative, and the answer is positive, you have overflow. So if the x3 is positive, y3 is negative and negative, but the sum 3 is equal to positive, then you have overflow. So this is how you can test it. So let's try to implement this piece of code here in our model, and try to simulate it again. So here, let's try to implement this. So let's introduce another output that is overflow, and then add this output, overflow, so, and then let's assign this overflow here. So assign overflow is equal to, we say this the last two summoners, so x3 and it with y3, and then negative of sum 3. Yeah, if it's negative, so the invert of that one. If that bit is on, we have overflow, or if we have a negative of x3, so the last summon of x3, and then AND it with the negative of y3, and sum 3. So this one should give us overflow bit here. So let's implement this overflow on the test bench file too. So we go to the test bench file and implement overflow bit. So we need a wire. So here, so it's test bench overflow. Try to implement here too. Overflow. Test bench overflow. And then we need to add this here too. So test bench overflow I need to add here to overflow. It's equal to percent 0 decimal. Yeah, so let's analyze and synthesize to see if we've done everything correctly. Okay, so we have some error here. Let's debug together. What is this error? Okay, line 30. Okay, we can see here we are missing this one. And one thing to be, because it's not Y that we are using, so first of all we didn't have the AND ports. So this is AND, and this is NOT, and this is OR. So we'd miss the AND here. And the secondly, this is not Y, because Y is the number we are putting, and then we need to add that the second complement of it, so which is this one. So we need to have it here. So that's what we are adding, and then let's try to analyze and synthesize now. Yeah, so let's go to our ModelSim. Go to library, nbit add sub. Let's update it, recompile it. And recompile the test bench file. And then restart the simulation. So we simulate it all again. Now let us try to find those examples that we have done on the whiteboard. The first example was 7 plus 1. So 7 plus 1, the answer is minus 8 in sign second complement, and this is wrong answer. That's why you have an overflow bit. So we can see the mechanism for the overflow bit detection is working. 7 plus 1 is 8, but the answer is shows is minus 8 because we have an overflow. The second example was minus 7 minus 2. So minus 2. Let us try to find minus 2. Here we have a minus 2. So it is 7. Minus 7 minus 2. Let's find minus 7. Minus 7 minus 2. You can see here we have wrong answer again. It shows us 7. It should be minus 9, but it is an overflow that we have an overflow bit detection. We can even try to look at the last example that we did on the whiteboard. It was 7 minus 1. So minus 1 is here. So 7 plus minus 1. You can see the answer is 6, and it's correct answer. So we can see here our design work correctly. We can try to look at the, for example, the minus. So here, for example, if you look at minus, let me show you something here on minus. For example, we have 0 minus 8. So we can see we have plus, it should be plus 8, and you can see it is out of range that we have overflow bit detection. So 1 minus 8, so that it is 9, but it's wrong answer here. It shows us is minus 7. It is an overflow bit detection. So we can see our overflow mechanism is working correctly. So on the next video, we'll try to implement this on board and see the workflow there.